So imagine you are standing in a bustling air traffic control room.
Right, highly stressful environment.
Exactly. The lights are, dimmed to reduce the glare on the glass.
Yeah.
Screens are glowing with hundreds of moving data points.
Yeah.
And the ambient noise is just this low, constant hum of intense focus.
Right.
And then suddenly, over the radio, a voice cracks through the static and says, ACC reports ALL deviation near controlled airspace.
Which, I mean, that is an incredibly dense packet of information to process.
It really is.
In a high-stakes environment like that, the cognitive load required to parse that sentence has to be as close to zero as possible.
And that is exactly what we are getting into today. If you're listening to this deep dive right now and you don't instantly know what that specific string of letters means, well, you're missing the underlying architecture of global aviation.
Yeah, you're already behind.
Right. Because communication in the sky, it can't just be rapid. It has to be ruthlessly precise.
Because ambiguity at, 500 miles per hour or in a highly congested terminal area, it compounds exponentially.
Oh, for sure. Every single syllable broadcast over an aviation frequency represents a calculated decision to minimize risk.
So we've aggregated a massive stack of sources for this deep dive. We're talking operational manuals, technical training documents, international standard pronunciation guides.
The heavy reading.
The very heavy reading. And our mission today is to deconstruct this alphabet soup, the sort of secret language of aviation.
Yeah.
We're going to look at the mechanical, acoustic, and the operational engineering that dictates exactly how pilots and controllers speak and operate.
And I think it's important to note that a lot of people outside the industry, they view these acronyms as just jargon,
Like a secret club.
Right, a way to gatekeep or just sound professional. But jargon is usually flexible. It evolves casually over time.
Yeah, slang.
Exactly.
Yeah.
But the aviation lexicon is the exact opposite of that. It is rigidly engineered, it's debated by international committees, and it's tested against the actual limitations of both human cognition and radio physics. Wow. Okay, so let's strip it down to the absolute foundation then. Before an aircraft even interacts with a radar screen, it exists as data. Right.
Yes, in a global logistical network.
Right. And the most common abbreviation you encounter across all these documents is just two letters, a /C, meaning aircraft.
A very basic building block.
Right. Now, at first glance, shortening a completely normal word, like aircraft, down to two letters, it seems like kind of an unnecessary shortcut.
It would be if we were just, writing prose.
Sure.
But /C isn't a shortcut. It's a fixed data string. Modern aviation relies heavily on centralized dispatch software, global technical logs, automated flight planning systems.
All interacting with each other.
Exactly. And in legacy database architecture, character limits were incredibly strict.
Oh, right.
Uniformity was essential for sorting algorithms. You can't have one dispatcher typing jet and another typing airplane and another typing Boeing.
The system would just break.
It would. It wouldn't know they were talking about the same thing. So normalizing the core subject to A/C means millions of flight plans and maintenance logs can be indexed and retrieved globally without search errors.
Okay, so it's about algorithmic uniformity on the ground.
Exactly.
But alongside that digital uniformity, the physical environment of the airport has its own strict coding.
Yes, it does.
Take the ABN, the aerodrome beacon. The manuals describe this as a rotating light signal guiding the aircraft to the airfield.
The lighthouse of the sky.
Yeah. But to me, that sounds like a holdover from the 1920s. I mean, we have synthetic vision systems now. We have GPS approaches that can literally auto-land a plane.
True.
So why is a spinning light bulb still a mandated piece of terminology?
Well, because a GPS coordinate is just an abstraction on a screen.
Okay.
An ABN produces physical photons that are actually hitting the pilot's retina. When you are flying an instrument approach in heavy weather, you're staring at the primary flight display.
Just looking at the screens.
Right. And the synthetic data tells you where the runway should be. But at a certain altitude, what we call the decision height, the pilot must visually acquire the runway environment to legally land.
You have to look out the window and actually see it.
Yes. And the ABN, which alternates green and white flashes for civilian airports, it provides immediate spatial orientation the exact second the plane breaks out of that overcast layer.
Oh, wow. So it bridges the gap between the digital instrument scan and the physical world.
Exactly. It resolves the cognitive dissonance of transitioning from staring at a glowing screen to flying visually at, 160 knots.
But you don't have time to scan the horizon.
No, you really don't. The ABN forces your eye exactly where it needs to be immediately.
Right, so you've broken out of the clouds, you've acquired the ABN. The critical metric now is your altitude.
Right.
But when you dive into the operational manuals, altitude is an incredibly fractured concept.
It is not simple.
No, it's not just a single tape measure.
Hmm.
The sources specifically contrast MSL mean sea level with AAL, which is
Right.
above aerodrome level.
Right, because MSL is a global fixed reference point. It's based on atmospheric pressure adjusted to sea level. But, you don't land on sea level unless you are flying a float plane.
Right, you land on concrete,
Exactly.
which, could be in Miami at sea level or it could be in Denver at 5,000 feet.
Yes.
So AAL is essentially resetting the tape measure to 0 at the runway threshold. It gives the pilot the exact distance between their landing gear and the actual tarmac.
Correct. The altimeter is calibrated using a specific pressure setting called QFE to display 0 right on touchdown.
Okay.
So it isolates the local vertical distance from the global topography.
Okay, that part is mathematically straightforward. But here is where the manual introduces a concept that completely changes the physics of the flight, ADA.
Aerodrome density altitude.
Right. It's defined as altitude corrected for temperature and pressure. Now, I understand that air density changes with weather, but why represent that as an altitude? I mean, if my altimeter says I am at 5,000 feet, I'm physically at 5,000 feet. The mountain next to me isn't getting taller just because it's a hot day.
The mountain isn't changing, no, but the aerodynamics of the aircraft are.
Oh, so
We use ADA because aeroplanes do not operate on physical geometry. They operate on fluid dynamics. Lift is generated by the mass of air flowing over the aerodynamic cord of the wing.
okay.
And thrust is generated by jet engines pulling in dense air, compressing it, and mixing it with fuel.
So if you are at that airport in Denver on a sweltering 100-degree summer afternoon,
The heat causes the air to expand significantly.
right,
The atmospheric pressure drops. The air becomes less dense, meaning there are literally fewer air molecules per cubic meter.
and the engines and the wings, they immediately notice that deficit.
Precisely. To the wing and the engine, the air feels exactly like the thin air you would normally find at, say, 8,000 or 9,000 feet. That is the aerodrome density altitude. The physical tape measure might say 5,000 feet AAL, but aerodynamically, the plane is performing as if it's thousands of feet higher.
Which radically changes the takeoff performance.
Radically.
If the air is that thin, the engines produce less thrust, and the wings need way more speed to generate the same amount of lift.
And that is the operational hazard right there. You have a reduced thrust lapse rate, and you need a higher velocity to fly.
Which takes runway.
Yes, that means you are going to eat up a massive amount of runway before the wheels ever even leave the ground.
Wow.
If a flight crew calculates their takeoff speeds, what we call their V speeds, like V1, VR, V2, and their thrust settings based on the physical elevation instead of the ADA, they might literally reach the end of the runway without enough lift to climb.
That's terrifying.
It is. ADA forces the pilot to quantify the aerodynamic reality, not just the geographic reality.
Okay, so the ADA dictates how quickly you can climb out of that local airport environment. And that climb gradient determines exactly how and when you enter the broader airspace, which means you are no longer the local tower's problem. You get handed off to the ACC.
The Area Control Center.
Right. And the manuals describe the ACC as the facility managing en route traffic. If the airport control tower is managing the physical parking lot, the ACC is managing the interstate highway system.
That's a good analogy.
But what strikes me is how they manage it spatially. Because they aren't looking at a window. It's an entirely radar-based polygon system.
Right. The airspace isn't just a big open sky. It is divided into a three-dimensional mosaic of sectors.
Okay.
And each sector is managed by an ACC controller. When you transition from the local terminal radar approach control up into the en route flight levels, the ACC takes over.
And they're doing a lot of math.
A tremendous amount. They are calculating the closure rates and spacing of aircraft that are converging from different continents at, 80% the speed of sound.
Right. And when an aircraft crosses the invisible boundary from one polygon sector to another, the ACC executes a spatial handoff.
Yes.
They switch the pilot to a new radio frequency with a brand new controller. It's essentially like a cellular network handing off a phone call as you drive down the highway,
Exactly.
just in 3 dimensions.
That's a really solid mechanical comparison. And to navigate through those specific ACC sectors, aircraft historically relied, and honestly, in many parts of the world, they still heavily rely on navigational instruments like the ADF.
The automatic direction finder.
Yes.
See, I want to dig into the ADF because the documentation explains it as a system that points toward a ground beacon.
Right.
But I want to know the how. How does a needle in a metal tube flying through thick clouds physically know where an invisible beacon is on the ground?
Well, it relies on the properties of AM radio waves.
Okay.
The ground station, which is called a non-directional beacon or NDB, broadcasts a low to medium frequency AM signal outward in all directions.
Like a radio station.
Basically, yeah.
Yep.
And the ADF equipment inside the aircraft utilizes two separate antennas to interrogate that signal.
Wait, two antennas? Why not just one receiver picking up the strongest signal?
Because a single standard antenna can tell you a signal exists, but it can't tell you the geometry of where it's coming from.
Oh, interesting.
The ADF uses a loop antenna and a sense antenna.
Okay, what does the loop do?
The loop antenna is highly directional. When the edge of the loop points directly at the beacon, the signal is strongest. But actually, the ADF system doesn't look for the strongest signal.
It doesn't.
No, it looks for the null.
The null.
Yeah, the point where the signal completely zeroes out.
Oh, because the null is a much sharper, more precise point of measurement than trying to find the, broad peak of a signal.
Exactly. When the flat side of the loop antenna is perfectly perpendicular to the radio wave, the signal cancels itself out.
Wow.
The system identifies that exact null line. However, a straight line has two ends.
Right, a front and a back.
Exactly. The loop antenna knows the beacon is on that line, but it doesn't know if it's in front of the aircraft or behind it. It's a 180-degree ambiguity. Ah, and that is where the second antenna comes in.
You got it. The sense antenna is omnidirectional. By mathematically combining the phase of the signal from the sense antenna with the signal from the loop antenna, the internal processor resolves the ambiguity.
So it figures out which way it's facing.
Right. It determines which end of the line the signal is originating from, and it drives the needle on the pilot's instrument panel to point directly at the physical station.
That is just an incredible piece of analog triangulation.
It really is elegant.
But, to fly these precise ADF headings and to navigate the polygons of the ACC airspace, the pilots and controllers have to actually talk to each other.
They do.
And this brings us to the operational hazard of VHF communication. Aviation doesn't use standard FM radio bands like a car stereo, right? It uses AM VHF, very high frequency.
Yes.
And that introduces a ton of atmospheric static.
It does. VHF is line of sight, so it is subject to terrain blocking, solar weather, and just general frequency congestion.
Right.
And the choice to use AM instead of FM is highly intentional. Wait, really?
Yeah.
If AM has more static, why use it for critical life-saving communication?
Because of something called the capture effect in FM radio.
A capture effect.
Yeah. If two people transmit on an FM frequency at the exact same time, the stronger signal completely dominates and suppresses the weaker one.
Oh, so you'd only hear one person.
Exactly. You would never even know the second person tried to speak.
Oh, wow.
And in aviation, that is a fatal flaw. You have to know if someone was cut off. AM radio allows for heterodyning.
Heterodyning.
Yes. If two pilots key the mic simultaneously, you hear this loud, squealing interference, but you can often hear both voices layered over each other.
Oh, so the static is a feature, not a bug.
Exactly. It alerts the controller that a transmission was stepped on.
That makes so much sense. But still, you have a communication system built on a frequency that guarantees static and interference, and you're trying to route planes through these complex ECC sectors.
Yes, which is challenging.
This is exactly why the ICAO, the International Civil Aviation Organization, they had to completely acoustic engineer the language pilots use.
Right. They couldn't rely on standard English phonetics. They had to create a lexicon that survives AM heterodyning.
And the rules surrounding acronyms versus initialisms are fascinating here. You have terms like NOTAM for notices to airmen, or METAR for the meteorological report.
Or TCAS for the collision avoidance system.
Right, and these are acronyms spoken as actual words, no HTAM, MEH, TCAS.
They are spoken as words because, linguistically, they contain strong, distinct formants.
Formants.
Yes, the acoustic resonances of the human vocal tract. A word like NHTAM has distinct, hard vowel sounds that literally cut through low-frequency VHF rumble.
Okay, but then you have other abbreviations that the manual strictly mandates must be spelled out letter by letter.
Yes.
Like the ground proximity system isn't GIPWAS, it's spoken strictly as GPWF.
Right.
and more importantly, the flight rules. IFR for instrument flight rules and VSR for visual flight rules. Why force the pilot to articulate 3 separate letters instead of just making it a spoken word?
Because if you try to pronounce them as words like iffer and viffer, you are relying solely on the distinction between the I sound and the V sound.
Okay.
And in acoustics, V and F are fricatives.
Fricatives.
Yeah, they are created by forcing air through a narrow channel in the mouth, which produces a high-frequency hiss.
Ah. And AM radios and aviation headsets, they frequently clip high-frequency audio to save bandwidth, right?
Exactly. Over a degraded VHF connection, iffer and viffer are acoustically indistinguishable.
Wow.
But the operational difference between the two is massive.
Well, completely.
VFR means looking out the window to avoid crashing. IFR means relying entirely on the instruments because you are blind in a cloud.
Confusing those 2 commands is deadly.
It is. So ICAO mandates separating them into individual letters with distinct phonetic shapes. India Foxtrot Romeo versus Victor Foxtrot Romeo. The acoustic contrast is engineered to survive the static.
That's brilliant. The manuals also point out the strict rule regarding altitude clearance. You never say the letters FL for flight level. You must speak the entire phrase, descend to flight level 30.
Again, it's about avoiding fricatives. The letter F in FL gets entirely swallowed by white noise.
Okay.
If a controller says, descend to FL 30, the radio clips the FL and the pilot just hears, descend to 30.
And they might interpret that as 3,000 feet instead of flight level 300, which is 30,000 feet.
Exactly. Speaking the full words, flight level acts as a multi-syllable acoustic buffer. It uses plosive consonants and hard L sounds to prime the pilot's brain that an altitude integer is about to follow.
It's linguistic armor. Every single radio transmission is armored against the environment.
That's a great way to put it.
But, here's the reality of our deep dive. Even with ADA performance calculations, even with ADF triangulation and this meticulously armored language,
Right.
the system is operated by humans. And humans fail. Components fail.
Sadly, yes. The entire architecture of aviation safety is actually built on the assumption that failure is inevitable.
And when failure results in an incident, a new set of acronyms takes over.
Yeah.
Specifically, investigation bodies like the AAIB, the Air Accident Investigation Board.
Yes.
Now, the natural human inclination, when a multi-million-dollar A/C goes down or there is a near miss in the ACC airspace, is legal liability.
Of course.
The public wants to know who is going to be sued and who is going to be fired. How do these investigation boards operate in an environment so heavily saturated by liability?
They operate by completely ignoring it.
Ignoring it.
Yes. The AAIB, the NTSB in the US, the BEA in France, their legislative mandate completely walls them off from the judicial system. They are legally barred from assigning blame or liability.
Which honestly seems counterintuitive. I mean, if someone made a mistake, shouldn't the investigation body hold them accountable?
If the goal is accountability, yes. But the goal of the AAIB is strictly diagnostic. They operate under a framework called just culture. If a pilot miscalculates their ADA or misinterprets an IFR clearance and they fear criminal prosecution, their primary instinct will be self-preservation.
Right, they'd hide it.
They will withhold data, they will obscure their decision-making process, and the root cause of the incident will be entirely buried under legal defense strategies.
So by stripping the investigation board of the power to punish, you basically incentivize complete transparency.
You extract the raw data.
Wow.
The AAIB answers 2 questions: the sequence of events and the mechanical or cognitive mechanism of failure.
That's it.
That's it. They analyze the flight data recorders, the metallurgical stress of the airframe, the exact phraseology used on the VHF tape.
Finding the actual flaw.
Right. Their findings are entirely forward-looking. They produce recommendations that force the ICAO to rewrite the phonetics or the FAA to redesign an ACC sector.
So the incredible safety record of modern aviation is entirely reactionary.
Yes. It is built on the forensic data gathered by boards who refuse to litigate blame.
They are essentially debugging the system.
Beautifully said.
So we've traced this entire architecture. We started with the foundational uniformity of A/C in global databases. We looked at how an ABN bridges digital displays to human retinas.
Right.
We unpacked how ADA mathematically alters the physical reality of altitude, changing how a plane accelerates into the sky.
Yep.
We saw how the ACC manages spatial polygons and how the ADF uses AM radio nulls to orient an aircraft. And layered over all of this is an acoustically engineered language designed to penetrate radio static and prevent fatal misunderstandings.
It is a vast, interdependent web. Every single abbreviation represents a solution to a historical failure.
This alphabet soup isn't jargon. It's a highly refined toolset designed to manage the physics of moving metal through the atmosphere safely.
It is a remarkable human achievement, truly. But, there is a massive technological shift happening right now that threatens the existence of this spoken language entirely.
Oh, really?
Yes. Modern aviation is heavily adopting CPDLC, controller pilot, data link communications, and digital ACARs.
Okay, what does that mean in practice?
It means instead of using their vocal cords to fight through AM static, pilots and ACC controllers are essentially text messaging.
Just typing to each other.
Yeah. Clearances, altitudes, and weather data are transmitted as silent digital handshakes directly into the aircraft's flight management computer.
Which I guess removes the acoustic ambiguity entirely.
Exactly. It is mathematically much safer. But as these digital pathways handle more and more of the routing, the VHF frequencies are becoming quieter.
Wow.
We are moving toward a future where the meticulously engineered syllables of NOH, TAM, and flight level may no longer be spoken aloud.
So the language of aviation might transition from this deeply human vocal tradition into an entirely silent exchange of code.
Leaving the sky completely quiet.
Wow. We'll leave you to mull that over on your own. Thanks for joining us on this deep dive.